Yeah. Last time we talked about a t-test, a t-distribution and t-test. First, let's do some multiple choice questions for review. Here, look at quiz 26, question 1. Most recent tests calculations estimate 95% confidence. Suppose that this is a maternal ancestor of humans believing. Yeah, what is meant by the 95% confidence interval in this context? Let's look at one. A confidence interval 2-8 mitochondria has been calculated. This curve. It is the case. Look at this. Let's look at this answers. Mm, confidence interval 2-8. So 95 the 20 random sample data, all the random data, uh, some of them are obviously wrong. So give me a second. D is obviously wrong. 20 random sample data attend this method and 95% intervals covered reach. The truth is, so we don't have any 20 samples. D is obviously wrong. How about C? 90. This is 95% probability that the mitochondria, if lived between 120,000 years and 156,000 years. This part is wrong. We don't have, the range is actually between these two numbers. Here's a C is obviously wrong. How about B? The confidence of the true age mitochondria has been calculated using t-score. We don't have a t-score here. Confidence interval is based on z-scores. And true confidence interval of the age has been calculated using the z-score 1.96. Let's check this one. 1.96, 1.96 z-score. We need the z table. Let's look for z table. Table of standard normal distribution. Standard normal distribution 1.96. 1.9 here. 1.96. This column 47.5, 47.5%, 47.5%. This is a percentage from the mean score 0 to 1.96 standard deviations above the mean. And so on one side, there's a 0.475. How about two sides? give me 0.475 times 2, that is 0.475 times 2, that is indeed 95%, 95%. So the number looks good. This 95% looks good, but is there anything wrong? Let's see. With this statement, confidence interval age was calculating z-score. Yeah, but this one's wrong. We don't have the z-score. We don't have the z-score for this age. We have this 95% interval. And the true answer is this one. Of all the random samples of data obtained by this method, 95% will yield intervals that capture the true age of the mitochondria if. This one, you just have to remember. Every time you have a question about a 95% confidence interval, what it means, you use this formula. Of all the random samples of data obtained by this method, 95% of the data will capture the interval of the true age of your interest. Look at number 2. Confidence interval estimate is determined from the GPA of a simple random sample of n students. All other things being equal, which of the following will result in a smaller margin of error? All right, smaller margin of error. What is margin of error? You have for any confidence interval, you have a confidence level, and you have an estimate, and then you have margins of error. A smaller confidence interval, will that give you a more a smaller margin of error? A smaller confidence interval, for example, we can say reduce confidence level from 95% to 90%. That's one. A larger sample standard deviation, will that give you a smaller margin of error? Smaller sample size, larger population size, smaller sample mean. You can see sample mean doesn't have anything to do with margin of error. The margin of error is not determined by sample means. The estimate have something to do with the mean of the sample. Your mean of the sample give you some idea about the population mean. So the last one is gone. Larger population size. Size of the population have nothing to do with the margin of error. And smaller sample size actually will give you a larger margin of error. If you are trying to make an estimate from a very small sample, you will make a larger margins of error. More likely you are going to make errors. Larger standard deviation of the sample? No. It's a smaller confidence interval. Smaller confidence interval will give you a smaller margin of error. So the margin of error has an inverse relation with how confident you are about your estimate. Increasing the confidence interval from 90% to 95% will give you larger margins of error. But reducing the confidence interval from 95% to 90% will give you smaller margins of error. Look at the number 3. 1 gallon of gasoline is put in each of the simple random sample of 30 test autos. You have a sample, simple random sample. This sample is 30 cars. The resulting mileage figures are tabulated. And the mean, this is sample mean. Mean of the sample is 28.5. Standard deviation, 1.5. And we want to determine 95% confidence interval estimate for the mean mileage of all comparable autos. You have a sample, you take a sample, and you want to know about the population, and you want to make an estimate about the population. So let's work on this one. Let me copy this one here. Well, actually, I might have it. I might have a Word file of this one. Let me check, double check if I have a Word file of this one. Maybe not. Let me just copy it here. So table, we might need that. We don't need this one. One gallon of gas. 1 gallon, so it's basically miles per gallon. On average, your sample of 28 vehicles, or 30 vehicles, have an average mileage of 28.5. Standard deviation is here, 1.2. You want a 95% confidence interval estimate. We just use the table to figure out the 95%. 95% on the on the Z table is corresponding to 1.96 Z-score. 1.96 standard deviations above or below the mean. So this is the boundary of your 95%. And now your sample mean is 28. Your best guess of your population, the best guess of comparable automobiles population is the same thing. So your estimated sample mean, population mean is 28. That is 28. And if you want let's see if I can find a normal distribution. We want to look at a normal curve. Now let's look at this normal distribution. Here I have a normal distribution. You have your mean. Your mean is 28.5. 28.5, this is estimated from your sample. And we have the boundary. Negative 1.96 and positive 9.6. Your confidence interval is between these two numbers. And you want to know what is the mileage corresponding to positive 1.92, 1.96, and negative 1.96. This would be your margin of error. So for confidence interval, we already got the estimate. The mean mileage is 28.5, which is the same as your sample mean. What we want to know is the margin of error. Margins of error is corresponding to the 1.96 standard deviations above the mean or below the mean. How do you do that? Again, to get the margin of error, you know the z-score and you know the mean. You want the standard deviation. Once you know the standard deviation, you will get the raw score, the mileage for the margins of error. You will get what is mileage corresponding to 1.96 standard deviation above the mean and below the mean. So we need to know the standard deviation. We don't have the standard deviation right now. We have to estimate that. And let's see, how do we want to estimate that? We don't have let's see, confidence interval. We don't have the standard deviation, so we have to estimate the standard deviation. How do we make the estimate of standard deviation? We have the sample standard deviation. We can estimate based on the sample. How do we do that? And let me look at the book again. Where's the Baron book? Yeah, we need to make the estimate of standard deviation. How do we make the estimated standard deviation? Let me close all these guys. Let's see. So we have the standard deviation of the sample is 1.2. How do we estimate the population? Standard deviation. Yeah, we need the estimated sample with a sample size of 30. Sample size of 30. So what do we do? And we know that when you have a sample size larger than 1, the standard deviation gets smaller because the variance gets smaller. So the estimated population standard deviation for sample means with n equals to 30. We do that. That is, you take the 1.2 squared, you square it to get the variance. Squared about to get the variance. Let's see. That is the variance you have. Let me get the calculator. So that is 1.2 squared, 1.44. 1.44, and the distribution of samples with sample size 30, so that's 1.44 divided by 30. 0.48. 0.48. This would be the variance. The variance of the distribution of sample means with a sample size of 30. And then to get the standard deviation of the sample means distribution, you get the square root. We get a square root here. Find a square root. Square root 0.48. So that'll be square root 0.48, 0.692, 0.693. Yeah, now you have the standard deviation. And so this standard deviation is estimated. We don't know the population standard deviation. So when you have an estimated standard deviation, you cannot use a z-score. You do not use a z-score. You need to use a t-score, t-distribution. T-distribution is very similar to the z-distribution, but have more scores in the tails, a less score in the middle. So we will need a t-distribution. T-distribution, to get the t-distribution cutoff, you need the degrees freedom. Degrees freedom, how many degrees freedom do we have? 30 minus 1. Your sample 30 minus 1, that is 29. And corresponding to the 95%, two-tailed, this will be two-tailed test. Why? Because it could be on either side. It could be on either side of the mean. So we would need to have a t-distribution. Do we want to have a t-distribution? Maybe not. So let's do a t-distribution. T-table. Too slow. Let's do it. Let's use the book's t-table. T-distribution critical values. T-distribution critical values. So here it gives you one-sided probability. Degrees freedom 29. Oh, we do have 29. And the tails, one-tailed, give you one-tailed. So you have 95% divided between the two parts. On each part in the tails, you need to have 0.25. Oh no, where is that? Here. 0.25 is the one you want on the tail. You want to have two tails, 0.25. Altogether, you have 95% in the middle. And 0.25 corresponding to 29, 2.045. So that cutoff will be a t-distribution 2.045. Make sure I get it right. 29, yeah. So that's the t-score cutoff. You want your t-score to be more extreme than 2.045. 0.045. And then you can calculate the t-value. T-value equals to 2 point, your mean is 2 point, no, sorry, 28.5, and you want to calculate your, so 2.5 plus, you want to add 2.045 times the standard deviation, 0.69, 0.693. So that's upper boundary. The lower boundary will be on the other side. You take it off. Negative 2.045. So this would be the margins of error you get. The key step is to estimate the standard deviation. Let's look at which one is a good choice. Question number 3. The 2.045, that sounds good. And then 1.2, that doesn't sound to be very good. So the standard deviation doesn't sound good, because here you have a standard deviation from the sample. That's not the estimated population standard deviation. This one's gone. 28.5, that's good. This is based on your sample estimate. The margin of error here, this is a t-score, 2.045 times the standard deviation. The key thing is about standard deviation. And then the next one, B, you have here 29. This is a sample size? No, not sample size. This is a degrees freedom. We don't use this one to get the standard deviation estimate. We use the 30. How about this one? 28.5, that is an estimate, and then 2.045, that is a t-score. This one sounds good. And you have this guy. This is estimate. This is estimated standard deviation. You have the sample standard deviation, and then you divide it by the square root of the sample size. We did it the roundabout way. So we first got the variance, and then the variance divided by the sample size, and then we took the square root to get the standard deviation. This one the same thing. And D and E are not right because of the 1.96. 1.96 would be the z-score. If you were using a z-table, this would be the z-score for cutoff, but we can't use a z-table. We need to use a t-table. Why? Because we are estimating this guy. We are estimating the population's standard deviation. We don't know the standard deviation. That's why we use t-score. You see the t-score cutoff and the z-score cutoff are quite close, because the t-table, the t-curve and the z-curve are very similar to each other. So this one is C is a good answer. Look at number 4. What sample size should be chosen to find the mean number of absence per month for school children. Let me copy this one. What sample size should be chosen to find the mean number of absence per month for school children within, here's the margin of error, 0.2, a 95% confidence interval. If it is known that the standard deviation is 1.1. You know the standard deviation is 1.1. And then what would be the number of people you need? What would be the n number? Let's look at the result directly. Number 4. Here, you need this guy. Now you are using the z-score. Do you use a z-score or a t-score? You use z-score because it is known. You know the standard deviation. If you know the standard deviation, you use the z-score. And you want the sample size. First of all, what do you know? You know the 95% confidence interval. That's what you want. And once you get the 95% confidence level, you know it's the z-score. The z-score boundary is plus or minus 1.96. This is 95% corresponding z-score. And you also know the margin of error. The margin of error is right here. Plus, this is margin of error. Plus and minus 0.2 times numbers of absences per month. We don't know the estimate. We don't know the average. We do not know the average. We have not learned the average yet, but we do know the standard deviation is 1.1. And then the question is that how many what's the number of people you will need to use to make the estimate? Here, we need to know that this one, 1.1 divided by the square root of n. What is this one? This one is estimated sample standard deviation. We know that 1.1, that is a population standard deviation, population of individuals. But now we have a samples. We have a samples with a sample size n. We don't know the sample size yet. We want to figure out what would be a proper sample size. At least how many people would you need to sample in order to get a decent estimate? And we know that the margins of error cannot be larger than 0.2. So that's one constraint. Margin of error cannot be larger than 0.2. So how do we get the margin of error? Margin of error here is 1.96 standard deviations. 1.96 standard deviations. That is margin of error. This can be positive and be negative. And this will give us an idea how to figure out the n, or at least what kind of n we need. Let's work this out. Let's work. Why do we, yeah, so here, the margin for error cannot be large. Margin of error must be smaller or equal to 0.2. How do we get the margin of error? The margin of error on one side, let's do the positive side, 0.96 times the standard deviation. So how do we get the standard deviation? We know the individual standard deviation is 1.1. 1.1, that is for individual scores, but we want samples of how many people? We don't know. Sample size we are trying to figure out. N, sample size equals to N. And so this one must be smaller or equal to +2. We are only working on one side, positive 0.2. How do we do this? So let's see. We need to, you see the n, the square root of n is here. We need to move it to the other side. Let's move the n to the other side. 1.96 remains here times 1.1 still here. We want to keep the sign the same, at least for now. So the square root of n goes to the other side. Square root of n must be larger or equal to this guy. Here 0.2, you got to move that. You got to move that to the other side. If you move that to the other side, to the left, you need to make it a denominator, divide by 0.2. And then this would give you an idea of n. Square root of n. And then once you get the square root of n, you can get n. Let's see, how do we get the n? 1.96 times 1.96 times 1.1 divided by 0.2. 10.78. We want to keep everything constant for now. Just calculate this part. This part is 10.78. Square root of n must be larger than or equal to 10.78. And then we want to get rid of the square root sign. So sign. And I want to move the n to the other side. N must be larger or equal to, we square the 10.78. 10.78 squared, 116.21. 116.2. In other words, you have to kind of sample at least 116 people, 116 to get a good estimate of margin of error. Determining the sample size is really a part or the important part of the game. Yeah. Number 4. Oh no. I'm going to go back to 26. Question 4. Question 5. Let's look at question 5. In a study aimed at reducing developmental problem in low birth weights, let me copy this one. Low birth weight babies. Low birth weight is defined under 2,500 grams. And you have a sample. 347 infants were exposed to a special education curriculum. Well, 561 did not receive any special help. After 3 years, children exposed to the special curriculum showed a mean IQ of 93.5, standard deviation of 19.1. The other children had a mean IQ of 84.5 with a standard deviation of 19.9. Find the 95 confidence interval estimate for the difference in mean IQs of all low birth weight babies who receive special education and those who do not. So here you have a difference. You want to estimate the difference between two populations. Population 1 is kids special education. Actually, low birth weight kids, low birth weight. And population 2 low birth weight kids receive no special education. The confidence interval between these two, the difference. We have samples. We have two samples. One sample is receiving, or the kids receive special education. Their IQ is 93.5. 93.5 minus, what is the other one? The other one is 84.5. 84.5, that's a pretty big difference. It's 9. The difference is 9. Or research hypothesis. What is a research hypothesis? We call the research hypothesis alternative hypothesis. Research hypothesis is mu1. Do I have the mu? I don't have the mu. The population, mean of population 1 is going to be larger than mean of population 2. Kids receive special education will have higher IQ than those who receive no special education. This is a research hypothesis. The null hypothesis is no difference. The two populations will have the same mean. And my data is here. My data is based on two samples. Sample 1 is from kids receive special education. Sample 2 come from kids receive no special education. Their difference is not 0. Their difference is 9 points. Would that be sufficient to show the difference between the two populations are not 0, are non-zero, larger than 0? This is what I'm trying to say. And we want the 95% confidence interval estimate for the difference in the mean. How do we do that? First order business, what curve do we use? Do we use a Z distribution or do we use a T distribution? ZOT. Well, ZOT. We use a T distribution. Why? Because we don't know the population standard deviation. We don't know the population. So here's the population. The difference between two means. What is the difference between two means? Two sample means. We don't know the distribution of this, the standard deviation of this distribution. We have to estimate that, estimate the standard deviation. That's why we use a T distribution. What is a standard deviation? Standard deviation, I mean the degree freedom. The degrees freedom for estimating the standard deviation is based on the sample size. Here we have two samples, right? Two samples. One sample is pretty big sample size. One sample is 347. The other one is 561. So that's a sample, the total sample size. So three, 4, 7. Sample size 347 minus 1. That's one standard deviation. The other standard deviation is, what is sample size? 561. 561 minus 1. That's a total standard deviation. 95%. We want to find the 95% interval. It's really a large sample size, really such a huge sample size. And the T distribution is going to be really close to the Z distribution. See here, then you go to the Z table, T table again. We might not have such large numbers, T distribution. 10, 30, 100. The largest one we have is 100 for the sample size, so degree freedom. And let's just use this one. One sample size, oh, this is T distribution value. 22, 50. This is between 100 and 1,000. 100, 1,000. Yeah. Where's the T distribution again? T table. We want the 95% interval. 95% interval. So that's two-tailed test. We have this one, 0.25, 0.25, 0.25. This here. Can't see this one. Something is missing here. Oh, here, 1 point. This one. 1.96 is almost the same. It's almost the same as the z-score. 1.96, 1.97 is between these two guys. Let's use 1.97. So the t cutoff is 1.97. And then we need to make the estimate. We need to make the estimate for the standard deviation. Let's look at what options we have. Yeah, so basically 93.5 minus 48.5. That's the difference between the two samples. The two samples differ by 9, basically the 9 points difference. And we know this part is good, 1.97. 1.97 is the t-score. The t-score we found out corresponding to the 95% interval with the degrees freedom, appropriate degrees freedom, very large degrees freedom. The question is that this part here. In this part, we are estimating the standard deviation. The standard deviation, which one is the standard deviation? It is a good estimate of a standard deviation. We have two samples here. One sample is 347, and this sample, you see, this sample have a standard deviation of 19.1. 19.1 is here. That looks very good. Looks promising. 19.1 squared, that is a variance of the sample 1. And then you divide it by the sample size. You divide it by the sample size, 347. That would be the variance of the distribution of means with a sample size of 347. The second part, 19.9, that is a standard deviation of the second sample, sample 2. You square it, get the variance, you divide it by the sample size, 561. These two are good. These are the two estimates of your sample variance. And then you add them together, that will be the variance of the difference between the two populations. Receiver special ed versus no special ed. And then you square root it. You get estimated standard deviation. This is estimated standard deviation of the difference between two sample means. This one is a good choice. What's wrong with this? What's wrong with the second one? This kind of one is not good. This one, no, 165, that was not good. The t-scores are wrong. The t-scores 165, right. All right, let's look at the next one. Non-subjects. You have 9 people, 87 to 96 years old, really old. And you give them 8 weeks of progressive resistance weight training. Yeah, you make them do weight training for 8 weeks. Strength before and after training of each individual was measured. Yeah, we don't care about left knee, right knee. So you have the data before, after. So each person has a before training weight, resistance, or weight. Well, strength, right? This is strength. After, before, after. This is pre-task, post-task design. You have pairs of data, and you get the difference. You get the difference between before and post. For this guy, increase was 4. 7 versus 3. 7 minus 3, that's 4. For the second person, increase is 13. That's a lot of increase. 15, 6, 12. Basically, you are interested in the difference between the 2 tasks, before the training versus after the training. And then here the major statistic, you calculate the average difference, between the 2 scores, the mean difference between the 2 scores. And you want to find out the 95% confidence interval estimate for the strength gain, basically for the difference. Between the after training and before the training. Here, 95%, the estimate. The difference is here, 11.6. This estimate is based on your sample. There's 8 people. There's 8 people you measured. The confidence interval is 95%. And your question is, here, what is margin of error? The margin of error is the one you need to calculate. How we do the margins of error. Now, let's review a little bit about the t-test. For this one, you're going to do the t-test for dependent means, dependent sample t-test. Yeah. Let's open the file. Let's open. T-distribution and t-test. Here it is. Here we need to do the t-test for dependent means. T-test for dependent means. The 2 scores are dependent on each other. T-test for single sample. T-test for dependent means. So here we have before and after. Before and after, we calculate the difference between the two scores, and then you get the standard deviation. So basically, we want the standard deviation. We want the standard deviation of the two scores. We get the means and we get the standard deviation. How do we get the standard deviation of the difference between these two guys? That's which one of these guys are correct. 3.03, 3.69, 3.76. That's the critical part. Here. The variance, so basically, you want to get the sum of squares of the difference. So here, sum of squares of the difference. And then you get the variance of the different scores. Once you get the variance of the different scores, you can get the variance of the mean differences. And then you can get the standard deviation of the mean differences. Coming back here, so here, different scores. Basically, this guys, these numbers, difference. Let's copy these numbers. These are the different scores. First, we need to get the variance of these different scores. Different scores, variance. So 1, 2, 3, 4, 6, 7, 8. How many people do I have? 8 or 9? Oh no, no, wrong place. 26. Nine people. So we have 9 people, and we have 9 differences. 9 different numbers. The mean is 11.6. Here, this one is the mean. The mean of difference, 11.6. And we want the variance of these 9 scores, these 9 different scores. What do we get? Here, let's look at, first you get the deviation. Probably it's a good idea to have a table here. Let's go back at the table. 1, 2, 3, 4, 5, 9. It's too large. Remember how you get the variance? How you get the variance? Same pattern. You always get the deviation. Deviation from the mean. So here, this one is 4 minus 11.6. 4 minus 11.6, negative 7.6. And how about the next one? 13 minus 11.6, 1.4. 15 minus 6, 3.4. 6 minus 11.6, negative 5.6. And then 12 minus 11.6, that's 0.4. 14 negative, so 14 minus 11.6, 2.4. 19 minus 11.6, 7.4. 7.5 minus 11.6, negative 4.1. Last one, 13 minus 11.6, that'd be a 1.4. So if you want to double check, seems to be right. And then once you get these deviation scores, what do you want to do? You want the squared deviations. Deviation. Square this guy. 7.6. 57.76. 1.4 squared. 1.96. 3.4 squared. 1.6. This one I'm pretty sure. 0.116. Seven, 6. 7.4 squared. 54.76. 16. 1.4, you got two 1.4, right? Because you got, no, this one's wrong. So it was 13 point, let me get this right, 13.5 minus 11.6, 13.5 minus 11.6, that's 1.9. So 1.9 squared. $361. This one's 1.6. Yeah, you got all the squared deviations. Now what do you do? You got the sum of square deviation. You sum all these guys, sum them up. Let's do that. 57.76 times x 31.36 0.16 576 54.76 18.81 1.96. Altogether, you have 185.74. That is the sum of square deviation. This is SS. Once you get the SS, sum of square deviations, this will be the mean. Once you get the SS, what do you do? Variance. SS divided by n minus 1. N 9 minus 1, that's 8. 23.22. All right, so that's a variance. This is variance of the data, variance of the sample based on the different scores. But now you want to estimate the variance of distribution of sample means. Here, this is variance. Variance of individuals, basically. But now you want the variance of sample means. That is 23.22 divided by what is the sample size? Now you divide it by 9. 2.58. 2.58. That's a variance. And then you want to take the square root, standard deviation. Square root 2.58, 1.60, 1.61, 1.61. Yeah. Let's look at what you got here. Basically, you got the standard deviation. You got the standard deviation. And you're looking for the confidence interval. Confidence interval. 95%, 95% two-tailed test. And then this is on the t-score. The degree of freedom, 9 minus 1, that's 8. 8 degree freedom. What is t-score cutoff? (95%). 95% on two sides. That'll be 2.5 on either side. Let's go to the t-table. T-distribution. We're looking here, this one. 0.25, 8, 2.306, 2.306. 2.306, that's a t-score. Same idea as a z-score. For z-score, you take z-score times standard deviation. For this one, you take the t-score times the standard deviation. One standard deviation is 1.61. So basically, the mean difference is 11.6. It's plus and minus 2.306 standard deviations times standard deviations here is 1.61. Let's see. 2.306 times 1.61, 3.71. Mm, 3.71. See which one is good. .71. This one, we are close. There's some rounding errors. 3.7, it's almost there. So we probably made some mistakes in the calculation. 3.76. But we got a 3.71. That's close. Yeah. Look at number 7. Company manufactures synthetic rubber, bungee hard. We don't care about this one. Just they make some things. The minimum, this is here. This is a critical thing. Breaking stress, 450 kilogram. This is solid information. This is what we need. We don't care about all those chords, whatever. If the mean breaking stress of a sample drops below a specific level, the production process is halted and the machinery inspected. Which of the following will result from a type 1 error? Oh, type 1 error. This one is a good question. See type 1 error. One, halting the production process when too many cores break. Is that a type 1 error? What is a type 1 error? Type 1 error is when the null hypothesis is true, you mistakenly reject the null hypothesis. So in this case, what would be the null hypothesis? Null hypothesis HO. Alternative hypothesis H sub A. If the mean breaking strands of a sample, if the mean of the sample drop before a specific level, the production process is halted and the machinery inspected. The research hypothesis would be there's a problem. The null hypothesis would be no problem. Type 1 error is you reject the null hypothesis when it is true. That is a null hypothesis. Let's look at the options. Is A type 1 error? Halting the production process when too many cores break. Is that error or is that a correct judgment? It's correct. When too many cores break, you need to hold the production. You need to check. How about B? Holding the production process when breaking strand is below specified level. Is this an error or is this correct? When the breaking stress is indeed below the specified level, you need to hold the production. That's not an error. So this is a good decision, correct decision. C, holding the production process when breaking stress is within specifications. Is this an error? Yeah, this is an error. The breaking stress is within specifications, no problem. There's no problem. This null hypothesis is good. But you are rejecting the null hypothesis. You stop the production. This is a type 1 error. And D is not. 7, good. Let's go 8. Coffee dispensing machine supposed to deliver 12 ounces of liquid into a large paper cup. A consumer believes that actual amount is less. There's an error. As a test, he plans to obtain a random sample of 5 cups. So sample is 5 cups. If the mean component is less than 11.5, he would reject the 12-ounce claim. If the average of the 5 cups is less than 11.5, he's ready to reject the 12-ounce claim. If the machine operates with a non-standard, you know the standard deviation. You know the standard deviation of 0.9. What is the probability that the consumer will mistakenly reject the 12-ounce claim, even though the claim is true? Here, this is an interesting question. Yeah. Here, the interesting thing is, the standard deviation. You know the standard deviation of the population, so you don't have to estimate it. Mean Z to T, ZOT. Don't use a T distribution or Z distribution. You got to use a Z distribution. Not T. You use a T distribution when you don't know the standard deviation. And what else do we know? So we need a Z. Let's get a table. So here, the mean is 12. On average, the mean is 12. That's a null hypothesis. And you want to reject the null hypothesis if the sample mean is 11.5. 11.5, so you need to get the proper curve. N5 the mean is 11.5. Sample mean, this is sample mean. The population mean is 12. According to the null hypothesis, this machine gives 12-ounce cups on average. And then your mean is the deviation is 11.5 minus 12 That is 0.5 ounces. That's the difference. And your question is that this 0.5 is negative 0.5 is how many standard deviations? How many standard deviations below the mean? And we know the standard deviation for the population is 0.9. 0.9. Population standard deviations 0.9. And you want to estimate the standard deviation sample means of the sample means. So you got let's see, we got a square root, so square root 0.9, you square it. Divided by sample size. That will give you the standard deviation. So here. Squared divided by sample size 5. 0.402. Yeah, this would be a standard deviation. One standard deviation would be 0.402. Your deviation is here, negative 0.5. How many standard deviation is that from the mean? The z-score? Negative 0.5 divided by standard deviation 0.402. 0.5 over 0.402, 1.24. That is 1.24 standard deviations. 1.24. The mean is here 12. And your 11.5 is 1.24 standard deviation below the mean. It's not 1 standard deviation below the mean. What is the probability that you would make a mistake? What would be the probability that if the true mean is still 12 cups, but you still get this kind of 11.5 ounce sample means? You find the proportion. You find the proportion of corresponding to 1.24. Now we can use a z distribution, 1.24. Is it 1.24? Yeah, 1.24. 39.25. 39.25. This 39.25 is from 1.24 to the mean in the middle part. But in this case, we are not interested in the middle part. We are interested in the tail. So the probability of interest is 50% minus 39.25. 50 minus 39.25, 10.75. So that's a probability. It's 10.745% probability that you will mistakenly reject the no-ounce claim, even though the true claim is true. Okay, question 8. Here you are using z distribution. All these t's are wrong. You know the standard deviation. You don't have to estimate the standard deviation. You use a z distribution. Which one is good? C and D both look pretty good, but one of them is wrong. C is wrong. Why? Because you're looking at the round tail. 11.5 minus 12, that's a negative 0.5. So you need to look at the other tail. You need to look at the small tail, the negative tail. This score got to be smaller than this one. 0.9 divided by square root of 5, that's n number. And if we get this calculated, let's get this calculated. So make sure we get the same result. Basically, it's 0.5 divided by 0.9 divided by square root of 5. This score is basically this part 0.9.
I have a question.
Yeah, go ahead.
Are you allowed to bring calculator to the
Yeah, you are. You need to bring a calculator. And you need to bring a strong calculator. Write this down. You need to get a Texas Instruments 84. 83 will also work, but shop around to see which one give you a better price. Texas Instruments 84. I say I'm using calculator all the time. 0.9 divided by square root of 5. Yeah, so that's 4.0402. Yeah, we get the same number. Right. Look at question 9. Fast food restaurant advertises as a large bag of French fries. Let's look at this one. French fries. It's about weight 150 ounces. Some people believe that they're getting less. Similar to that question, and they got a scale. They weigh 15 bags. Sample size is 15. What is the conclusion of the sample mean? Sample mean is 145. Standard deviation is 1281. Here, what is the conclusion? What are we getting here? The mean, let's see. According to the Null Hypothesis, what will the population mean? Population mean would equals to 150 grams. That is what the restaurant claims. But then what evidence you got? Evidence is n equals to 15. Mean is 145.8. Standard deviation of this sample is 12.81. You have one sample. And this is one sample t-test, or t-test for a single sample. Why do you use a t-test now? Because you don't know the population standard deviation. You know the population mean is supposed to be 150 grams, but no standard deviation. The standard deviation needs to be estimated based on your sample. This is your sample standard deviation. So you use a t-test. You use a t-test for a single sample. How do we get a t-score? In other words, we need to get a t-score. See the t-score. Let's calculate the difference. Difference is 145.8 minus 150. 145. 4.2. Negative 4.2. Basically, the sample is not 150. It's 4.2 grams lower than 150. And you need to calculate this as a t-score based on this one, based on this 2.4. You need the population standard deviation. Population standard deviation estimate. Well, we call it standard error. Better call it standard error. Standard error is the estimated population standard deviation. How do we do that? So you want where's standard deviation 12.81, 12.81. Let's get a square root sign. For standard deviation, you need to get the square root. What's inside the square root sign? 12.81, you square that. You square this standard deviation. To get the variance. And then you divide it by sample size, 15. Let's see. That's a standard error. Square root 12.81 squared divided by 1/5. 3.31. That's a standard deviation. And then you get your t-square. How many standard deviations are you below the mean? Negative 4.2 divided by 3.31 standard deviation. 4.2 over 3.31, 1.27 negative. .27 standard deviations below the mean. That's a t-score. And then look at the options. There is sufficient evidence to prove the fast food restaurant advertisement is true. No, this one is wrong. We cannot prove that the claim is true. We can either reject the null hypothesis or not reject the null hypothesis. But we never say that we prove the null hypothesis is true. No, that's not good. B, sufficient evidence to prove, no, this one is not good either. Every time you see the word proof, is wrong. Number C is more reasonable. Students have a strong evidence to reject the fast food restaurant's claim. Basically reject the null hypothesis. Do we have enough evidence to reject the null hypothesis? let's try look at the t value. So basically, we look at what kind of probability is associated with the t value. Degree freedom. Degree freedom is 15 minus 1, 14. So with 14 degrees freedom, see what kind of cutoff we have. T distribution. Well, we do a one-tailed task. We do a one-tailed task. We use a 0.05 level. Degree freedom is 14. 14 degree freedom. So make sure this is a 0.05. 14 is 1761. 1761 cutoff. We call it critical value. Critical value 1.71 negative. And then we look at the t value we computed. Is that more extreme than the critical value or cutoff? No. So we do not have enough evidence to reject the null hypothesis. We do not have enough evidence to reject the restaurant's claim. D would be right. Yeah, see if we can do one more. Maybe not. 26. Nine. 10. Let's do this one. This will be a short question. Given an experiment with no hypothesis, mu equals to 35. Alternative hypothesis, mu smaller than 35. And the possible correct value of 32. You obtain so what's here? Missing something. A possible correct value of 32. You obtain sample statistic 33. After doing analysis, you realize the sample size n is larger than you first thought. Which is the following result from knowing with increased sample size? Increasing sample size. Now this one is complex. This one needs some time to figure out. Yeah, let's stop here, guys. I've recorded the first 9 questions. Recorded the first 9 questions on quiz 26. I'm going to go post this video today, and your assignment is to do the first 9 questions. Work out the first 9 questions in quiz 26 at least.
Okay, sure. Yeah.
All right.
Okay.
Have a good weekend.
Have a good weekend.